Hey everyone, and welcome to this explainer. Today we're going to unpack something absolutely fascinating, the hidden language of our modern world. Have you ever actually stopped to think about how our digital devices interact with the physical universe around us? Well, today we're going to trace the journey of a signal and totally demystify how sensors and transducers actually work.
So just imagine this problem for a second. The real world we live in is entirely analog, right? We experience continuous flowing changes in heat, pressure, humidity, sound. It's a constant stream of physical energy. But the computers, the microcontrollers, the digital systems that run our entire lives, they are completely blind and numb to all of that. They only speak one language, ones and zeros, electrical signals. So how exactly do our digital systems feel this physical world? How do we cross that massive divide?
Well, here's our roadmap for today. We'll quickly cover translating the physical world, sensors versus transducers, the anatomy of conversion, measuring transducer performance, the enemies of accuracy, and then wrap up with some really cool real-world applications.
Okay, let's dive right into this. Section 1, translating the physical world. Moving right along to Section 2, sensors versus transducers. In any measurement system, we have to process non-electrical physical quantities using electrical methods. And the line between the devices that do this is actually a huge point of confusion in engineering, but it's really quite distinct. A sensor is simply a device that detects a physical parameter and reports it in any form. Think of the mercury in a classic glass thermometer. It moves when the temperature changes. It senses the heat and gives you a mechanical readout. But a transducer, that acts as the ultimate translator. Its specific job is to take that non-electrical quantity, like heat or pressure or motion, and convert it directly into an electrical signal. The transducer is what bridges that critical gap between the physical and the electrical. All right, Section 3, the anatomy of conversion. Let's peek inside that translator.
Picture a complete data acquisition ecosystem. It's brilliantly structured. You have data being collected by a whole variety of sensors. Some are non-contact, like a camera or a radiation detector. Some are passive, meaning they generate a signal without even needing external power. And some are active, which means they actually require an excitation circuit just to turn on. All these different signals travel through interfaces. They get combined in what's called a multiplexer. They're translated by an analog to digital converter. And finally, they feed into the computer brain. It's literally an entire ecosystem built around gathering analog data.
Now, let's zoom way in from that macro system down to the micro level of the device itself. A complete transducer basically relies on two key components. First, you've got the sensing element. This is the part that actually feels the physical change. Second is the transduction element. This takes that feeling, that response from the sensing element, and actively converts it into a proportional electrical signal. And sometimes, which is super cool, one element elegantly performs both of these jobs at the exact same time.
Which brings us to Section 4. Measuring transducer performance. So, once we have our translator, how do we know if it's actually doing a good job? Well, we use a rule of 3 to evaluate it, starting with input characteristics. This is all about the type of input and the operating range. But the absolute most vital concept here is minimizing what we call loading effects. Ideally, a transducer shouldn't steal energy away from the thing it's trying to measure. Imagine sticking a room temperature thermometer into a tiny hot cup of liquid. The thermometer actually cools the liquid down slightly while it's measuring it. It's literally stealing energy. That is a loading effect. To prevent this electrically, the device must have a very high input impedance so it doesn't extract force or power from the input signal.
The second metric is transfer characteristics. Think of this as the core rulebook the transducer follows. It's governed by the transfer function, which is just the exact mathematical relationship between the physical input and the electrical output. This also involves the device's sensitivity, like how much does the electrical output change for every single unit of change in the physical input. We want a highly predictable, mathematically sound translation, not like a human translator who might randomly decide to add their own creative spin to a sentence, right?
The third metric is output characteristics. The final electrical output, whether that's voltage, current, or impedance, must be fully compatible with the next stages of your digital system. And just as we wanted a really high input impedance at the start, here at the end, we want an ideal output impedance of practically zero. This ensures the transducer can easily drive the signal forward, acting perfectly as a constant voltage or current source without loading down the rest of the system.
Section 5, the enemies of accuracy. Time to meet the villains of our story.
Unfortunately, the physical world doesn't always cooperate, and our devices face unavoidable engineering errors that inevitably distort our translations. But we can group these into a pretty digestible framework. First, we have scale errors, where the device just deviates from its transfer function. Then, dynamic errors. These happen when the physical input changes rapidly, but internal components cause a time lag. Next is noise and drift, which are just random, unwanted signals that contaminate the output. And finally, environmental influences. This is where stray electromagnetic fields, humidity, or ambient temperature shifts totally mess with our device's accuracy.
Actually, let's briefly touch upon how scale errors uniquely manifest, because they're pretty fascinating. You might see a zero error, where your scale is just off by a constant factor across the board, or a sensitivity error, where the deviation grows proportionally. Nonconformity means the output gets distorted in a weird, nonlinear way. But the absolute most intriguing one is hysteresis. This is when the device actually remembers past inputs. It's almost like it holds a grudge. If you increase the temperature from 0 to 50, you get one curve. But when you decrease it from 50 back down to 0, the device follows a completely different curve. It gives you mismatched readings for the exact same temperature just depending on which direction you're coming from. Wild, right?
Okay, Section 6, Real-World Applications. Let's anchor all this theory into reality.
Let's connect back to everyday life with the classic oral thermometer. This is a purely mechanical sensor. The liquid mercury inside the glass tube expands as your body heat increases. It pushes up a calibrated scale, converting the invisible physical quantity of body heat into a visual expansion that we can easily read. It's simple, it's elegant, but remember, it doesn't give us an electrical signal.
So let's see how this builds into something digital. Enter the thermocouple. Unlike that mechanical thermometer, the thermocouple is a true transducer. It's made by simply joining two dissimilar metals together, and when you heat that sealed junction, a magical thing happens. It directly generates a voltage. It converts that heat energy straight into millivolts of electrical signal, completely bypassing the need for any mechanical readout. And you can see the practical genius of this concept in a standard household furnace control module. The heat from the pilot light is sensed by a thermocouple. That heat actually causes the gas inside the thermocouple tube to expand, and this expansion pushes a diaphragm that mechanically keeps the critical gas valve open. If the pilot light goes out, the thermocouple cools down, the gas contracts, and the valve snaps shut, preventing a dangerous gas leak. It is a brilliant, fail-safe application of sensing physical changes.
So, to summarize our core takeaway today, transducers quite literally make the invisible visible. Without these incredible translation devices, the rich, dynamic analog data of our universe, every single vibration, every shift in temperature, every ray of light would remain completely invisible and inaccessible to our modern digital infrastructure. They are the essential bridge between nature and computation.
And I'll leave you with this final thought. Technological progress is now allowing us to manufacture these devices on a microscopic scale using EMS technology. They are smaller, faster, and infinitely more sensitive than ever before. So as these microscopic transducers are increasingly embedded into everything from our cars, to our clothes, to our own bodies, what invisible web of smart sensing are you going to interact with tomorrow? Thank you so much for exploring this with me on this explainer. Stay curious, and I'll catch you next time.